Hi, my name is Sanjeev Singh, and I want to talk to you about a program called Maritime Autonomy that is about robust relative navigation and control for aircraft, both fixed wing and rotary wing, landing on ship decks. Near Earth's core business has to do with developing autonomy for VTOL aircraft. And by that I mean we develop the sensors, the computing, and algorithms that are necessary to enable aircraft to fly safely and efficiently on their own. We currently have ongoing programs with various branches of the military and engagements with a large number of aerospace and end user companies. To date, Near Earth has conducted roughly $50 million in government-funded R&D and an extra $10 million in commercial R&D. We have a team in Pittsburgh of 80 full-time employees supporting multiple programs focused on aerial autonomy, and we have access to a large number of test sites, including an airfield just north of Pittsburgh where we test a lot of our programs. We've been working with aircraft all the way from sub-meter scale to 3-meter scale, and then more recently at 10-meter scale, such as a full helicopter. All in all, we have accumulated about 2,000 hours of flight testing in varying conditions and scenarios. The key challenge we expect to meet is a requirement for autonomous navigation that would enable safe and reliable aerial operations between ships and between ship and shore. Our eventual transition target is the MQ-25 Stingray, but there are several transition opportunities available that are possible in the meanwhile, especially with rotary wing aircraft. The expectation of our program is that we can provide reduced size, weight, power, and cost that could be mounted to a large number of VTOL airframes, and that can provide optimized multimodal perception systems for robust operations. As you can see, there are applications in both fixed wing and in rotary wing aircraft, in where these aircraft need to very robustly and accurately need to know where they are with respect to the ship that they're landing on. The key operational need that we hope to address is supplying new forward operating bases ahead of the arrival of Marines, resupplying existing forward operating bases and combat outposts, and resupplying various kinds of ships en route with supplies brought in from other ships or even from shore. The key improvement that we see is that with this technology, there is a decreased loss in personnel in case of accidents or enemy attack, potential to operate without constant human supervision, potential to operate beyond line of sight that increases the reach of supply chain, and more efficient supply chain by utilizing diverse aircraft classes tailored to specific mission requirements. And as I've mentioned before, there are applications in both rotary wing and in fixed wing aircraft. We have developed a sensing and computing suite that's shown in this picture here that enables trajectory planning, en route obstacle avoidance, landing zone evaluation, and relative navigation that uses long wave infrared, EO cameras, ultra-wideband ranging, and then scanning LiDAR. This is all in the form of a suite that weighs about 10 pounds and could be attached to many different aircrafts to provide these key autonomy capabilities. Our system has evolved from a large ONR-sponsored program called ACUS from 2012 to 2017 that automated a full-scale UH-1. At the end of the program, we took the key ideas and sensing modalities and converted that into the prototype that I showed before, and have used that to test on slow-moving targets. Our Phase 2 objectives are to do system development such that we can mature the ship relative navigation that's already been done in Phase 2. We'll do a ship-based closed-loop system demonstration using a relevant UAV and a ship, and create a simulation that shows a 6-DOF model for use in NAVAIR's virtual testbed suite with an ending TRL of 6. In this slide, we show some of the sensing modalities that are resident on the computing and sensing payload. The top left is a thermal image that shows the detection of the ship from quite a distance as the aircraft is approaching. The ship deck is usually a very warm spot on a relatively cold sea and provides a bearing to the ship, even in degraded visual environments. On the bottom left is a EO image that shows how any of the landing markings on the ship deck can be detected, and the aircraft can get a full 6-DOF relative pose as it approaches the deck. At the bottom is a point cloud that is reconstructed from the scanning LiDAR, and what this gives is not only a relative position to the ship deck, but also some idea as to whether the landing surface is clear. On the right is an EO image that is picking up infrared beacons at known locations, and this can be also used to compute relative navigation in the form of a 6-DOF solution. We believe that the most relevant transition advocate is PMA 262, with its need for persistent maritime unmanned aircraft systems. For next steps, we propose to continue characterization and advancement of system performance and capabilities, and to support a field demonstration in a relative marine environment. Our market analysis shows applications on both the defense and the commercial side. On the defense side, there is a great applicability to autonomous helicopters that are expected to perform a majority of the supply operations. And on the commercial side, we expect that the drone delivery market will be approximately $25 billion by 2030, with about 100,000 aircraft needed. Major package delivery and supply chain management companies have started to test drones, and we expect that some version of this technology could be used there. In addition, the urban air mobility market is projected to be roughly $15 billion by 2030. We're looking for both avionics suppliers and aircraft OEMs as transition partners to bring this technology to the market. The value proposition that we can provide is that our technology will enable unmanned aircraft to operate out of ships of various sizes in degraded weather and visibility conditions, and to enable individual hardware and software modules to be improved or replaced individually without impact to overall system capability. While I've been speaking about technology that is specific to shipboard operations, Near Earth is actually developing a broad ecosystem of capabilities for unmanned aircraft, starting with mission planning before the aircraft starts flying, obstacle avoidance to detect and avoid static objects, collision avoidance to detect and avoid other aircraft, GPS-denied navigation to fly in cases of jammed or degraded GPS, contingency management to be able to deal with unexpected circumstances while en route, landing zone evaluation to make sure that the aircraft is able to land safely, and then precision landing to be able to land by quick specification from a person on the ground. Now, these are key capabilities that we are developing separately. They can be integrated or they can be modular. At the bottom is a link where you can see some information about our company and some videos of systems that we have developed. Please feel free to reach myself, Sanjeev Singh, or John Banani at Near Earth. Thank you.